The scripts and project source code are in the description. This is technically a part 2, so watch this video first if you want to replicate this effect. So, to make these 3D caves, we first have to understand this simple algorithm. So here's a crash course on procedural map generation. What you're seeing is a very simple algorithm called the random walk, or the drunkard's walk. The name describes it perfectly. It has those names because that's how it works, randomly and drunkenly. The Godot icon is the drunkard who stumbles in random directions. If the drunkard ever walks into a wall, they knock it down, like a drunk Godot Kool-Aid man? It's that simple. Again, listen closely. The drunkard moves in random directions and deletes any walls it touches. Move, delete, move, delete. That's 90% of it, and the basis of quite a lot of map generation in 2D. Let's formalize that slightly. Number 1, we start the drunkard at a position. Number 2, choose a random direction to travel in. Number 3, check that space. If there's a wall there, delete that wall. Number 4, move into that space and update your position. Number 5, we repeat this until we're satisfied. This could be a certain number of movements or a certain number of walls destroyed, whatever you like. Once more, for simplicity's sake, we move randomly and delete walls we touch. Move and delete. Pretty simple. Armed with this knowledge, the industrious among you could probably start making map generation in 2D with no issues. If you like 2D tile-based games, the basic backbone of how their maps are made. To adapt this for 3D, it is pretty much the same thing, except now we move the drunkard in all 3 dimensions, X, Y, and Z, and remove volumes instead of 2-dimensional walls. Here's the world from our previous tutorial filled with voxels. This pink ball is the drunkard. As you can see, we're just stumbling around in random directions and removing spherical volumes around its position. Simple as that. Just like in 2D, move and delete. Let's speed this up a little bit and put it underground. Alright, now let's see what it looks like when we generate it instantly and increase the number of iterations so we get bigger caves. So we're currently getting these nice long tunnels, but they're a bit round and unrealistic, right? This is due to only subtracting with spheres that are perfect spheres. Caves typically have more interesting, jagged, or bumpy formations. To improve this, we can actually start adding small chunks of geometry in every removal step too. We'll raycast out from the drunkard in every step, and if we hit a wall, instead of removing a sphere there, we'll add a sphere of geometry at that wall. This adds a nice cavey effect. Here's what it looks like slowed down. The next step is adding some random variance to the sphere volumes that we use for terrain manipulation to make things look less uniform. And finally, to place things on the walls of the cave, we can just save each of the drunkard's traveled positions in an array, and then, after cave generation is complete, we revisit those positions one after the other and raycast out randomly from them to place objects along the walls. And that's it, folks. That's the entirety of the approach I've come up with for the sake of this tutorial. This is performant and effective, but there's enormous room for customization with this system. Quick note before the follow-along. This is not exactly what Deep Rock Galactic does for their cave generation. While the voxel system is reasonably similar, they first use nicely designed pre-made rooms that are connected by tunnels after being placed. That kind of hybrid system, part handcrafted, part procedural, is often the best experience for players. But this is still a good foundation to start from, and mastery of these concepts will allow you to make all kinds of cool procedural games in 2D and 3D. Alright, that's the theory. If you want to make exactly what I made, here comes the follow-along. Alright, so I had originally intended to do a walkthrough, but this is a bit of an intermediate topic, so instead I'm going to do an overview of the code and the changes I've made, because it's a little bit too much just to try to make every single change on camera and still have this be quick. So, the first thing that I've done is remove the player, and here we have this camera 3D, which we use instead. In the asset library, I picked up this simple free look camera for Godot 4, which is just going to give you a script. This will allow you to navigate in the world like you would in the editor, which is going to be much nicer for actually looking at our caves. So I just removed the player, added this camera 3D. You need to, of course, make your voxel viewer a child of the camera 3D to do this. But that's that. Apart from that, in the voxel terrain, we've changed a little bit of stuff. Namely, we've made the height 100 instead of 0. So this places us underground now because the floor or the crust of this world is 100 meters above us now. So that's going to make it much easier just to have underground caves. We have added a material or an XPath shader to our material, which is just an outline shader that'll be in the description. None of this has changed except I've increased the triplanar sharpness because that'll just make the blending look a little bit cleaner. And of course, we've changed the world environment. So here's what I've got right now, all the settings. So you can copy this if you want. And of course, this will be in the project, which you can download, but you can pause this and take a look. Okay, that is that. So let's talk about the cave generator. So the cave generator is in Node 3D. It has a child right now, which I've instantiated separately. It's just a basic marker, marker 3D, which I've called start marker. We place it underneath the cave generator because it tells the cave generator where to actually start generating the cave. The first little chunk of cave to be removed will be started at the actual start marker here. And that's that. So let's jump into the cave generator. We'll see that over here I've created a bunch of exported variables, which I will discuss now. So just like in the previous tutorial, we have to get the voxel references here so that we can make edits to the terrain. So that's what we do. Again, we get the start marker, which is over here, so that we can tell our stuff where to start. The current walker, if we go into the actual cave generator scene, is this mesh here. This doesn't mean anything. This mesh here, which is just a purple ball. It really doesn't mean anything. It's just for visual's sake, so you can watch things kind of iterate around. This is just our drunkard. This is what holds the position and what we'll be moving around, so we just get a reference to it. The random walk length is very important. This is the number of iterations that you want to use for your cave. So increasing this will decrease increase runtime, but it will give you longer and longer cave systems. Removal size is a very interesting variable. Removal size is used throughout to determine kind of the base unit for additions and removals of geometry. So for example, when we add a sphere or remove a sphere, each of those spheres is going to have a radius of 2 at its base. The ceiling thickness is a variable we use just to prevent our drunkard from going up and up and up and reaching our floor and creating an entrance to the cave on the crust. But you can change that if you want that to be different. The crystal preload, can I get this to go away? Yeah. The crystal preload is just a instantiated or a packed scene that we use for placing these crystals on the wall. And the random walk positions is a variable that we use to store all the positions that our drunkard visits, just like we discussed. So in the setup, which is what we do first, we simply set our drunkard's position, or its full transform, to the start marker's position, or its full transform. Easy as that. We have something here that checks for input, which is this cave gen input, which I have on R. So when I press R, it does 100 iterations worth of cave generation. So let's get into the actual random walk. Here's the meat. So we use a for loop here. This is for our number of iterations again, random walk length. So for I in range 100 currently. We are going to move the random walker to this new position. This new position is going to be dictated by, of course, a random direction. So let's talk about the random direction function. There are two ways of getting this. One is a much higher accuracy direction vector, much higher accuracy, just direction in general, because we use floats here to determine the x, y, and z coordinates of this direction. The other one, we just use -1, 0, and 1 for the x, y, and z, which will get you more directions than 9. I don't know why I have that there. The other thing we do, or we can switch between them by using this parameter useFloat. The vector with magnitude variable here, we multiply our direction vector by the removal size in order to give our direction a little bit of magnitude, so that when we add it to our position, we're moving in the correct scale with the removal size. So basically we get a random direction, and then we add that random direction to our global position, so we move. We clamp the y value of our global position, again to prevent us from going above ground. We do that by clamping the y value. This is just a very low number, so this could be infinitely low if you wanted it to be. And then we subtract the height, or subtract the ceiling thickness from the height in order to give us a value we do not want to cross on the y. Whenever we move, we want to store our current position in the random walk position so that we can visit it later. And once we've done that, we can carve out a chunk of terrain at our current position. So let's check out this function. Just as before, we tell the voxel tool to remove, and we are going to remove a sphere's worth of voxels at our current position. The sphere will be a little bit different. We're going to be using removal size, but removal size is its own function that has this variance parameter, which very simply is going to change the removal size a little bit. So with a variance of 1, nothing will change. If you have a variance of 1.25, then you can expect your removal size to be changed by negative, or to be 25% larger or 25% smaller. So we get some nice variance doing that. So we've carved out some chunk. Now we need to raycast to add geometry to make things look a little nicer. So we need to get a point on the wall. The voxel tools comes with its own special voxel raycast, which is very nice. So tons of ways to do this, but we'll use the voxel tool one because it's apparently pretty performant. You raycast out from our position. We're going to get a random direction for this raycast, which is cool. Again, we're using the float version, so it's a true random position, and this is the length of the raycast. So we shoot out a raycast with a length of 20 in a random direction. If we hit something, then we return the position of the hit. If we don't hit anything, then we return null, because we don't want to do anything if we hit null. So if wall point, which is saying if we actually have a position, so not if it's not null, then we want to do a sphere addition at that wall point. So sphere addition is just like subtraction. We change the mode to add instead. We have a couple of parameters here. Okay, so I realized that was a little bit of a superfluous function, so I just cleaned it up a little bit. So it's do sphere of addition takes in a point in 3D space, which we know is going to be a point on a wall, and then we use the voxel tool addition mode instead of subtraction, and we do a sphere's worth of addition at that point. We get a removal size, and then I make it currently 2 times smaller than the removal size. This is a bit of a magic number. It should probably be removal size. Just so that you actually make a little bit of progress. You can experiment with all these things. You choose the values that you think are good, but these are what I have. It gives me the best visual space. Okay, so now we've added a point, and all that we have to talk about now is the wall additions pass. So this happens once this for loop is completed. So after we've carved out the entire cave, we're going to revisit the random walk positions. So 4 walk positions, so let's get the first one. Again, we're going to raycast just like in the other function. We're going to get some point on the wall, and then we're going to do a very standard instantiation of a node, which is our crystal preload, which we discussed earlier. Well, you can add it to ourself. I just deleted that little chunk because it was kind of pointless. So we do an interesting thing here. Of course, we need to set its position along the wall. We do some variation on the scale just for the visual's sake. And then in order to orient it correctly, What we do is we use the lookat function to have it look at a point that is opposite, or not opposite, a little bit ahead of the actual wall's normal. I wish I had a diagram to display this, but this is just a handy way of getting things that you place on walls to look away from the wall instead of into the wall. And honestly, folks, I believe that's it. Let's run this, and we can hit R. Might take a second, and that'll load. We see the outline shader. And look at that. So really, it's quite simple. It really is quite simple. You can see it's quite large. Quite large indeed. I believe my settings are a little bit higher. This might be 1,000 iterations or even 2,000. But you can do a ton with this. Thanks for watching. If you like no-nonsense tutorials, please consider liking and subscribing so I know to make more. See ya.